Hi, I will continue with section 6.3. I will finish it today. This is a continuation of the section on rational numbers. So we're going to start working with mixed numbers. In working with rational numbers, you could get an answer such as 123/8. So a rational number such as this, in which the numerator is greater than the denominator, is called an improper fraction. Although the answer may be correct in its present form, you may have to think a little to understand the size of this number. However, if we divide 123/8 to get the quotient 15 and the remainder 3, then we see that 123/8 is 15 and 3/8, which is not quite 15 and a half. Okay, a number like 128 or 123/8. This is an example of a mixed number, of an improper fraction. And if we divide 123/8, so if we do the division, we get a mixed number. So that's an improper fraction, and that is equal to 15/3/8. This is an example of a mixed number. Okay, so they show, I'm not going to copy this, I'm just going to read it. They show you the procedure for converting an improper fraction to a mixed number. So to convert the improper fraction A over B to a mixed number, perform the division, and then write A over B as Q R over B, where Q is going to be the number of integers, which is going to be the quotient. Q is going to be the quotient, and R is going to be the remainder. So we're going to, in the next example, we're going to convert the following improper fractions to mixed numbers. Okay, we start with 51/6. So that's an improper fraction with the numerator greater than the denominator. If we want to convert this to mixed number, we just perform the division. Okay, so we know that 6 times 8 is 48. And then 51 minus 48 is 3. The quotient is 8, and the remainder is 3. So 51/6, it's 6. It's not 6, it's 8 and 3/6. And we can always simplify the fraction part. 3/6, you know that this 1/2, so this is the same as 8/1/2. So that is going to be the mixed number. And B, convert the improper fraction 144/11 to mixed number. So let's do the division. So 11 times 1 is 11. And 11 times 3 is 33. Okay, so the improper fraction 144/11 is 13 and 1/11. So that's going to be the mixed number. That's going to be the improper fraction converted to mixed number. And if we go the other way around, if we want to convert a mixed number to an improper fraction, we just add the fractions. So these are different examples. These are new examples about converting a mixed number to an improper fraction. So we are going to start with 4 and 4/9. So if we want to convert this to an improper fraction, all we do is add the fractions. 4 plus 4/9. 4 is the same as 4/1. The least common denominator is going to be 9. So we need to multiply. We need to multiply 4 by 9 plus 4. 4 times 9 is 36. And 36 plus 4 is 40. And part B, convert the fixed number 8 5/13 to an improper fraction. We again just add the fractions. 8 plus 5/13. The least common denominator is 13. And then 8 times 13 plus 5. 8 times 13 is 104. Plus 5 is 109. And 109 is not a multiple of 13, and 13 is a prime number, so we cannot simplify this further. Okay, so rational numbers have the property that the decimal part either terminates or repeats. So I'm going to go over example 9 to show this property. Okay, so I'm copying this example. Okay, we're going to write each of the following rational numbers as a decimal number. That's on page 265. Okay, so 5/8. We're going to do this with a calculator. Part A. So 5/8. Just put this in a calculator and you will find that this is 0.625. If you do 7/16, 7/16, if you put this in a calculator, that's going to be 0.4375. Now let's try part C. We're going to do the division. 82 divided by 111, and we'll see one property of rational numbers. Okay, so the numerator is less than the denominator. Whenever that happens, we add a 0. We have one decimal point. We need to multiply by 7. And the remainder is 43. If we keep on going, we add a 0. We need to multiply by 3. That's going to be 97. And then add another 0. We need to multiply by 8. So 970 minus 888 is going to be 82. Okay, so we are again. So if we do that, let's say we wanted to add another 0. The thing is that we are again dividing 820 by, or 882 by 111. So that cycle will continue. And let's write an arrow. Okay, so we are again dividing 82 by 111, and we're going to get another sequence, 738. And that process will keep repeating, 738, 738, 738, and so on. So one way to write 82 over 111 in decimal form is 0.738, 738, 738, and that that sequence will keep repeating, or 0 point. You can indicate the repeating part with a bar on top. So I'm going to copy this part of the text. Rational numbers have the following property. Or I'm just going to type it. So I'm going to type this part. In general, when writing a rational number in decimal form, we always get either a terminating expansion or an infinite repeating expansion. So in the first two examples, we got the first case, that the decimal expansion terminated. And technically that repeats, but with a sequence of zeros. So in A and B, it terminated, and in part C, the decimal part repeats. So keep repeating forever. Okay, so we're going to, so we're going backwards. We're now going to write rational numbers as a quotient of as quotients of integers. So we're going to start with A. We have a rational number whose decimal expansion terminates. So all we need to do is write the decimal part divided by 1, and the same number, the number of zeros is going to be the number of places after the decimal point. So I'm going to write like this. Now we learned, so that fraction is correct, but it's better if we can simplify it. We learned from the divisibility rules that both numbers are divisible by 4. Because the last two digits of 3,468 is 68, which is divisible by 4. So that number divided by 4 is 267. And also a number that ends at 00 is divisible by 4. 10,000 over 4 is going to be 2,500. Okay, so far we have 267 over 2,500. The question is, can we simplify this even further? So let's check. 267, that is divisible by 3. We know that it's divisible by 3. So 267 divided by 3 is 89. And 89, let's see. Okay, making sure that this is correct. So we got 260. Okay, I made a mistake. That's 867, which is still divisible by 3. Yeah, but I'm making a mistake. So that's 867. That's still divisible by 3. And 867 divisible by 3. I'm checking this quickly. So that's 289. And 289 is 17 times 17. And for this matter, 2,500 is not divisible by 3 or 17. From the divisibility rules, we can see that it's not divisible by 3. And you try to divide 2,500 by 17, you'll see that the remainder is not 0. So this is not divisible by 3 or 17. So that's going to be the rational number as a quotient of integers, and that's as much as we can reduce. Okay, in part B, we have a rational number with a repeating expansion. Looks like this whiteboard froze. So that's how, okay, let's try again. Okay, so the next one is a rational number with a repeating expansion. We're going to write the rational number 0.51 or 51 repeating as a quotient of 2 integers. So this is what we do. We're going to call, we haven't seen any algebra, but this is still doable. We're going to call x equals 0.51, 51 bar. That is 0.51, 51, 51, and so on. If that happens, then 100 times x is going to be 100 times 51, 51, 51, and so on. So that's going to be 51 point, and the decimal expansion will look the same. So we're going to subtract these two to get rid of the decimal part. So we're subtracting 100x minus x. So 100x is 51 point, a sequence of 51s, and x is 0 point, a never-ending sequence of 51s. So 100x minus x is going to be 99x. And whenever we subtract 51.515151 and so on equals 0 point, a sequence of 51s, the decimal part cancels out, and 99x equals 51. And at the end, x is 51 over 99. We can reduce this fraction because both 51 and 99 are divisible by 3. 51 over 3 is 17, and 99 over 3 is 33. So at the end, 0.51 equals 17 over 33. So that's going to be the rational number as a quotient of integers. And I will finish this section with an application. I'm copying this from the book. We're going to do number 80 on page 269. Okay, so Adrian is building a cabinet for his new audio system. He will use a special West Indian mahogany for 2 sides and the top. If the side measures 2/3 feet, and the top measures 3/4 feet, how much mahogany will he need? Okay, so that's going to be 2 sides and the top. So 2 sides measure 3 2/3 feet each. And one top measures 3/4 feet. So how much mahogany will he need? We need to add 3 2/3. We had 2 of those, so that's 3 2/3 plus 3 2/3 plus 4 3/4. 3/4. But if we are going to add fractions, we need to convert those fractions to improper fractions. So 3 2/3, it's 3 plus 2/3. Common denominator is 3. So that's 9 plus 2. And that's 11/3. And 4 3/4. So that's 1. And 4 3/4. Common denominator is 4. So that's 19 over 4. Okay, so we have converted the mixed numbers to improper fractions. This is equal to 11/3 plus 11/3 plus 19/4. The least common denominator of 3 and 4 is 12. So that's the least common multiple of 3 and 4. Actually, let's simplify another thing. 11/3 plus 11/3 is 22/3. And now we can use the least common denominator of 3 and 4, which is 12. 12 over 3 is 4, so we need to multiply 22 by 4. And 12 over 4 is 3, so we need to multiply 19 times 3. 22 times 4 is 88. And 19 times 3 is 57. 88 plus 57 is 133. So that's 145. And we can finally convert this fraction to a mixed number. And the reason to do that is because that's going to give us a better idea of how much material we need. So 145 over 12, that doesn't tell us much. But if we convert this to a mixed number, that's going to give us more information. So 145 over 12. Okay, so we need to multiply 12 by 1, and then multiply 12 by 2. Okay, so 145 over 12 is, and I'll make this a little bit bigger so you have an idea. That's going to be 12, 112 feet. So that gives us better information of how much material Adrian needs. Or what is the same, or 12 feet and 1 inch, because in 1 foot there are 12 inches. So that answers the question of the problem. That's the amount of material that he will need. I'm going to stop here. Thank you for listening.